Steelmaking in the melt shop begins by charging scrap metal into an electric arc furnace, where high-voltage electric arcs generate intense heat to melt the charge. Oxygen is injected to reduce carbon content, and fluxes like lime are added to remove impurities, forming slag. The molten steel is tapped into a ladle and undergoes secondary refining in a ladle furnace, where temperature and chemical composition are precisely controlled. Degassing may be applied to reduce hydrogen and nitrogen. Once refined, the steel is cast into billets, blooms, or slabs for further processing. The entire operation demands extreme heat and power. The production of railway wheels at the Allegro facility is a process that transforms steel blanks into durable components for rail transport. The process begins with solid steel blanks supplied by Evraz. These blanks are first heated in a rotary hearth furnace to approximately 1,250 degrees Celsius. This high temperature softens the material, making it suitable for forming operations. Once the blanks are sufficiently heated, they undergo descaling to remove oxide layers and impurities from the surface. This step ensures better material flow and surface quality in subsequent processes. The descaled blanks are then positioned into a 10,000-ton hydraulic press for performing. This press shapes the steel into a rough wheel form, preparing it for precise rolling. Next, the preformed blanks are transferred to a state-of-the-art wheel rolling machine developed by Schuler. In this stage, the blanks are rolled into the desired wheel profile. The rolling operation is especially critical in forming the wheel tire, the outer running surface, which must meet strict dimensional and mechanical specifications to endure high loads and wear in service. After rolling, the wheels proceed to a crimping and piercing press with a force of 5,000 tons. This final forming step refines the geometry, creates the central bore, and strengthens the wheel structure. Every wheel then undergoes a geometric inspection, using a laser-based measurement system to verify accuracy and compliance with design standards. Once approved, each wheel is permanently marked in a marking press for traceability. Finally, the wheels are heat-treated to enhance their mechanical properties. The running surfaces are specifically hardened to resist fatigue and wear, ensuring long service life under demanding railway conditions. The process starts with raw wheel blanks, stored before rough machining on CNC vertical lathes, which remove the forged oxide layer and shape the wheel's profile. Full immersion ultrasonic testing is then conducted to detect internal defects. The wheels proceed to finish machining, where high-precision turning operations refine critical geometries such as tread, flange, and bore, according to design tolerances. Surface hardness is measured using an automatic Brinell or Rockwell hardness tester. Static balancing is performed with a vertical centrifugal single-plane balancer to ensure stability during rotation. Accepted wheels are automatically marked for traceability. Fluorescent magnetic particle inspection is used to identify surface cracks. For special applications, oil hole drilling, web plate hole machining, and internal bore grinding are executed using dedicated equipment. All data is recorded in the system for quality control before the wheels are cleaned, packed, and dispatched. The machining process using the 5-axis machining center ensures accurate and efficient metal cutting. The workpiece is clamped on a dual-supported rotary table, offering excellent rigidity and accuracy. Machining occurs simultaneously along the X, Y, and Z axes, each controlled by optical scales for precise positioning. The A-axis tilts from 30 degrees to -120 degrees, and the C-axis rotates continuously, both driven by high-performance cam systems with direct rotary encoders. The spindle, rated at 3.5 kW and reaching 15,000 revolutions per minute, accommodates ISO 40A63 tools. During operation, feed rates range up to 15,000 millimeters per minute, while rapid movements reach 48,000 millimeters per minute, enabling efficient roughing and fine finishing. This setup supports complex geometries and multi-sided machining in a single clamping. The aluminum wheel machining process involves a robot-integrated and high-accuracy sequence to transform cast aluminum blanks into finished wheels. The process starts with robot-assisted loading of the raw wheels onto the Puma VAW800 vertical turning center. This machine performs both rough and finish turning on the inner and outer wheel faces, including the hub bore and rim surfaces. The high spindle speed and rigid structure of the VAW800 ensure excellent surface quality and dimensional accuracy. After turning, the wheel is automatically transferred to a vertical machining center, such as the Meinx 5400 and DNM 652 with a rotary table. These machines conduct drilling of bolt holes, valve holes, and perform pocket milling or slotting based on the wheel design. For more complex contours or decorative patterns, the VC 635 axis machining center is employed to machine intricate profiles in a single setup, reducing repositioning errors. The Puma AW560 may be used for additional fine boring or facing operations. Throughout the entire line, robot automation manages all loading and unloading tasks, enhancing productivity, repeatability, and operator safety. Its modular design, the system which can include machines like the Puma Vi8300, offers scalability for different wheel sizes and styles, making it ideal for high-volume aluminum wheel production. The Repcon shear forming machine uses 2 servo-driven rollers to shape conical copper parts with extreme precision. Position readers ensure micron-level accuracy. This advanced process is essential for manufacturing anti-tank ammunition components with open angles from 10 degrees to 80 degrees. The drilling process on the AK Drill 1 APD machine begins with securing the material onto the T-channel clamping table, which has 8 points of contact. This method minimizes vibrations, preventing any tool wear and significantly extending the lifespan of the tool tips. By securely holding the material, the machine ensures greater precision during the drilling process. Once clamped, the machine starts the drilling operation. The plate drilling machine is equipped with a high hole drilling capacity of 11.8 inches, 300 millimeters, enabling it to handle thick materials with ease. This capacity allows the machine to drill larger holes faster and more efficiently than standard machines, which reduces production time and increases overall productivity. The step cutting feature allows the machine to handle drilling tasks regardless of the material height. This ensures that even parts with varying thicknesses can be processed without the need for manual adjustments, making it ideal for complex projects. The machine also offers the capability to perform additional tasks such as countersinking, tapping, and chamfering, enhancing its versatility in metal processing operations. To maintain tool efficiency and ensure consistent results, the APD features an automatic tool changer with an 8-station tool holder. This system allows for quick and seamless tool changes, eliminating the need for manual intervention. In addition, the in-tool fluid delivery system combines high-pressure air and coolant to prevent overheating of the tool while cleaning the chips from the tool tip. This cooling system helps increase tool longevity and ensures smoother operation, improving overall machine efficiency. The machining of a sprocket from 42 Chromo 4 steel is carried out using the Quaser MF4000C vertical machining center, equipped with a Siemens 828D control system. The process begins with securing the workpiece, a forged or pre-machined blank of 42 Chromo 4, onto the machine's table. The maximum swing diameter for this setup is 400 millimeters, accommodating the size of the sprocket. Initial roughing operations are performed using a robust SK40 spindle system with big plus face contact, providing superior rigidity and stability. During rough machining, the spindle operates at a speed of 4,244 revolutions per minute, with a feed rate of 800 millimeters per minute along the C-axis and a depth of cut up to 22 millimeters. This stage removes the bulk of the excess material quickly and efficiently, preparing the sprocket's profile for more precise finishing operations. Tool changes are executed by a 30-position double-arm tool changer, achieving rapid switching times of just 4.5 seconds. This minimizes downtime and enhances machining productivity. The system supports high-speed spindle rotations of up to 5,730 revolutions per minute for certain cutting operations, delivering high efficiency during both roughing and semi-finishing passes. Following the roughing process, the machine transitions to finishing cuts. These are conducted with reduced depth of cut, around 10 millimeters, and increased spindle speeds, up to 5,730 revolutions per minute, along with a faster feed rate of 1,200 millimeters per minute on the C-axis. The aim here is to refine the sprocket tooth geometry and surface finish to meet final specifications. For certain internal or lubrication features, such as the incorporation of lubrication grooves, high-speed spindle rotations are utilized. These grooves are machined at speeds up to 6,000 revolutions per minute, using specialized tooling to ensure precision. The vertical machining center SK40 motor spindle delivers a torque of 85 Newton-meters, ensuring sufficient cutting force for machining the tough 42 Chromo 4 material. Throughout the process, the machine's high rapid traverse speed of 36 meters per minute supports efficient tool positioning and non-cutting movements, contributing to the overall cycle time reduction. The synchronization of high spindle speeds, rigid tooling interface, fast tool changes, and dynamic axis movements demonstrates the versatility and performance of the machining center when machining high-strength alloy steel components like sprockets. The process ends with a final inspection of the machine sprocket to ensure all dimensional tolerances, surface finishes, and functional features like tooth profiles and grooves are accurately achieved. Spindle is manufactured entirely in-house by Heller on a dedicated, climate-controlled spindle production line. The process starts when an automated storage system supplies raw parts to the first station via a driverless transport system. Initial soft machining gives the components their basic shape. Next, the parts are heat-treated own hardening facility to achieve maximum wear resistance, CUNT. After hardening, the components are precision machined down to micrometer accuracy. Throughout the production process, the parts move through a flexible flow line. Internal and external cylindrical grinding machines provide the final geometry, achieving extremely tight tolerances. Measurement data is collected online and analyzed to control process stability. High-precision measuring equipment inspects the components for deviations below 1/1000th of a millimeter. If a part meets all criteria, it is deburred, packaged, and stored in a lift system. Assembly begins in a one-piece flow layout. A technician assembles all components step by step, supported by an automated storage system that provides the correct parts. After assembly, the spindle undergoes balancing and final inspection to ensure smooth rotation. A QR code links the spindle with its measurement data. The finished spindle is now ready for installation in a Heller machining center. The MIG-MAG narrow gap welding technology efficiently joins thick metal plates by minimizing weld seam volume by up to 60%. Using a rectangular blade, it precisely guides the wire, gas, and coolant. This reduces welding time, filler usage, and energy, while ensuring high-strength, high-quality seams. The construction of the Explorer yacht at the Damon facility in Antalya begins with modular block assembly. Steel hull sections, including the bow and engine room blocks, are prefabricated and reinforced to meet ice-class standards. These blocks are lifted and positioned using cranes, with careful weight calculations ensuring safety. In parallel, aluminum superstructure blocks are built off-site and integrated later. The engine room, built separately, is installed during the megablock stage. Once the steel and aluminum structures are joined, interior outfitting begins. This includes installation of systems, wiring, insulation, and H2 yacht design bespoke interiors across 3 guest decks. Specialized zones like the D13 certified helideck and tender garages are precisely constructed with reinforced supports, Throughout the process, naval architects and project managers collaborate with headquarters in the Netherlands through regular site visits and remote meetings, ensuring tight quality control. Final stages involve mechanical system integration, sea trials, and luxury finishing. The construction of metal buildings begins with custom design using computer-aided systems, enabling fast, accurate structural planning. Steel coils of varying thickness arrive at the plant. Some become structural frames, others form purlins, girts, or pre-painted exterior panels. Plasma cutters shape flanges and webs, which are welded into frames by automated machines. Roll formers shape lighter coils into roof and wall supports. Once fabricated, all components are delivered to the site for assembly by trained builders. The use of standing seam metal roofs offers weather tightness and long-term cost savings. This efficient, eco-friendly system reduces raw material waste and shortens construction time by 1/3 compared to traditional methods. Engineers first designed the composite rocket fuel tank using advanced modeling techniques. The manufacturing process began with automated fiber placement, where resin-impregnated carbon fibers were precisely laid onto a large mandrel to form the tank structure. This technique minimized material waste and improved strength. Instead of traditional autoclave curing, the team used out-of-autoclave methods, significantly reducing cost and complexity. Layers were built up to form the cylindrical body and domes. After curing, components were trimmed and assembled. Engineers then applied special coatings and integrated fittings. Leak-proofing techniques, based on lessons from earlier tests, were implemented to eliminate microscopic leaks. The final 18-foot diameter tank was prepared for cryogenic hydrogen testing at NASA Marshall Space Flight Center to validate its performance under extreme conditions. Emulsion explosives, detonators, and booster charges are manufactured using high-precision equipment. Raw materials are mixed, sensitized, and packed into cartridges or bulk containers. Final products undergo strict quality control before delivery to mining and industrial sites. The assembly of the DMU-600G involves a meticulous and well-organized process. First, the machine bed and column are installed, followed by alignment of the rotary table and the large diameter guideways. The spindle head, weighing several tons, is carefully mounted using overhead cranes. Each axis is then equipped with precision drive components and linear scales. Electrical systems and control units are integrated, and the entire structure is rigorously calibrated. The assembly includes the integration of the tool changer and chip conveyor system. Final testing ensures high dynamic performance and machining accuracy of this large 5-axis gantry milling machine. At Junkovitz Hydraulics, the assembly of hydraulic cylinders is a precise and technically sophisticated process that ensures optimal performance, durability, and customization. The company manufactures both standard and block-type hydraulic cylinders, with working pressures ranging from 100 to 500 bars, and piston diameters between 16 millimeters and 200 millimeters. The assembly begins with the selection of the piston rod, a critical load-bearing component. Depending on the application, the rod is made from standard hard chrome steel 20 MnV6, 550 to 800 N per square millimeter tensile strength, or induction hardened chrome-plated steel 38 MnV56, 850 to 1000 N per square millimeter tensile strength. Diameters range from EU10 mm to EU100 mm, with surface treatments conforming to ISO 9227 corrosion resistance standards. For heavy-duty applications, rods up to E200 mm made from materials are used. The cylinder barrel is manufactured from honed, seamless, or welded tubing, compliant with 10,305 or 10,220 standards. These tubes are honed to H8, H11 tolerance classes to ensure smooth operation and proper sealing. Internal diameters span U 25 mm to U 250 mm. These tubes are cut to length, cleaned, deburred, and internally inspected before integration. Following this, pistons are fitted with advanced sealing systems, including groove rings, two-piece seals, wiper seals, and compact seals. These ensure tight sealing under high-pressure conditions. Guide rings and wear strips made from PTFE bronze or other high-performance materials are mounted to maintain alignment and prevent metal-to-metal contact. The cylinder head and end cap are then machined and assembled. Depending on the design, components such as threaded or weld-on rod ends, spherical bearings, and self-aligning bushings are incorporated. Mounting options are versatile and comply with ISO 12240, accommodating clevises, trunnions, and flange types. Advanced configurations may include inductive position sensors, external or internal feedback systems, and end-of-stroke cushioning tailored to customer requirements. These features allow for precise control and integration into automated systems. Once the internal components are assembled, the piston and rod assembly is inserted into the cylinder tube. The cylinder is then fully sealed and torqued according to specification. After assembly, each cylinder undergoes pressure testing, typically above its maximum rated pressure, to check for leakage, proper seal performance, and functional integrity. In conclusion, the hydraulic cylinders produced by Jankovitz Hydraulics are engineered and assembled with meticulous attention to material quality, dimensional precision, and customization. This ensures that each unit can perform reliably in industrial, mobile, and specialized hydraulic applications. The spiral welded pipe manufacturing process begins with strict inspection of raw materials. The strip is leveled, trimmed, cleaned, and pre-bent before entering the forming line. Using internal or external control rolls, the strip is helically formed. A precision gap control device ensures accurate weld alignment. Shrub maggot arc welding is performed on both sides by electronically controlled welding heads. Flux temperature, humidity, and flow rate are tightly controlled. All weld seams undergo continuous ultrasonic testing for defect detection. Pipes are cut into single lengths by air plasma cutters. Finally, pipe ends are machined to ensure precise bevel angle, blunt edge, and perpendicularity. Completing the process, pipeline construction involves multiple coordinated stages. First, the stringing route places pipes in sequence, and inspectors verify joint numbers. Pipe ends are beveled using a pipe facing a chine to prepare for welding. The main gang preheats the pipe over 100 degrees Celsius to remove moisture, then aligns the internal welding chine for the root pass. Subsequent welds are completed, including hot pass and fill passes, followed by ultrasonic testing to ensure weld quality. Once welding is done, coating begins. The oxidized weld is sandblasted clean. Then, the coating shack containing the coating head is lowered onto the weld. The head applies an epoxy mixture to protect the joint. Temperature is carefully controlled during this stage. After coating, the coating head is retracted, and the crew moves to the next weld. Elsewhere, pipes are bent using a mandrel to prevent buckling. Finally, side booms lift coated pipes into position, and backhoes dig ditches for installation. The generator stator rewind process begins with bar removal and core cleaning to eliminate aged, inefficient components. Next, new stator bars are installed and carefully tied and brazed to ensure structural integrity and electrical conductivity. Insulating caps are added for protection, followed by blocking installation to stabilize components against vibration. Finally, a thorough electrical test verifies performance and reliability. This process prevents cooling failures and performance issues, especially in hydrogen or air-cooled generators. With expert planning, reverse engineering, and quality workmanship, the stator is restored to optimal condition, ensuring safe, efficient power generation and minimal downtime. The Toshiba F-Class generator delivers 150 to 230 megawatts output, ideal for 1x1 combined cycle gas turbine systems. It features a compact single-cylinder, single-flow steam design that simplifies installation and reduces size. Advanced technologies such as optimized steam path, supersonic last-stage blades, and sensitive sealing enhance efficiency and durability. The generator uses indirect hydrogen cooling for better performance and lower maintenance costs. An F-Class insulation system improves heat dissipation, enabling a smaller, more reliable stator. It also includes a brushless excitation system with a permanent magnet generator for increased reliability. Sliding bearings with a forced lubrication system ensure stable operation and long life. With superior materials and smart engineering, the Toshiba F-Class generator offers high efficiency, easy maintenance, and exceptional reliability. Anodizing is an electrochemical process that transforms the surface of aluminum into a highly durable aluminum oxide layer. Unlike paint or plating, this finish is integrated into the metal, making it resistant to peeling, chipping, and corrosion. The process begins by immersing the aluminum in an acid electrolyte bath while an electric current passes through it. At low temperatures, this controlled oxidation forms a hard, porous layer that can be dyed or sealed for additional properties. Aluminum is ideal for anodizing due to its natural oxide-forming tendencies and wide industrial use. Hard anodizing, in particular, creates a thicker, wear-resistant surface suitable for demanding environments such as defense, construction, or high-end consumer products. It also enhances electrical insulation and corrosion resistance. Sealing the anodized surface improves corrosion protection, but may slightly reduce hardness. Because of its long-lasting finish, low maintenance, and excellent appearance retention, anodized aluminum is widely used in applications like electronic casings, trays, loudspeakers, and lighting fixtures. The construction of the Bibo Arch Tunnel for the A9 diversion involves the use of precast concrete segments. The arches are produced off-site, using molds that allow for circular, depending on project requirements. Begins with preparing the foundation at ground level, avoiding deep excavation. After leveling and positioning the base slabs, the precast arch segments are delivered and lifted into place using cranes. Each segment is precisely aligned and placed side by side, without the need for falsework or temporary supports. The self-supporting nature of the arches allows for rapid progress. Once the full arch span is assembled, the joints are sealed, and backfilling begins immediately. Road construction can proceed directly on top of the arch. This method reduces installation time significantly and minimizes road closures or detours. The absence of expansion joints also ensures long-term durability. The fabrication process began with the construction of the claw heavy-duty steel framework, including the oversized jaws that form the core lifting mechanism. These jaws were precision fabricated to ensure structural integrity under extreme loads and subsea conditions. Versabar custom-built large steel baskets, referred to as cradles, to support fragile topsides during recovery. These cradles were designed with lifting flexibility capable of being hoisted either by the claw directly or through a rigging system featuring two specially fabricated support pipes. The claw and cradles underwent rigorous testing before the first successful lift. Controlled by the VB10000, the claw demonstrated high efficiency and flexibility in subsea operations.